Welcome to the deep dive. Today, we are taking a bit of a historical voyage back to the 18th century.
Yeah, a time when, believe it or not, the biggest scientific puzzle wasn't, splitting the atom or anything like that.
No, it was something that sounds almost mundane now. Just knowing where your ship actually was on the vast ocean.
Exactly. It sounds so simple with GPS on every phone, right?
Yeah.
But for centuries, finding your east-west position, your longitude, was this desperate, deadly gamble.
So in this deep dive, we're digging into the sources to unpack that whole struggle. The massive prize Parliament offered.
The competing ideas and really the story of this, well, this unlikely genius who finally cracked it.
All right, let's break it down. Latitude and longitude. We have those lines on the map. Latitude, the horizontal ones, the parallels. Sailors kind of had a handle on those, right?
Yeah, latitude is, you could say, a gift from nature.
Mm-hmm.
You've got the equator, the tropics. These are astronomically fixed.
Defined by the sun's path.
Right. So a sailor could measure the angle of the sun at noon, or maybe Polaris, the North Star above the horizon. And, well, with some tables, you can figure out your latitude pretty reliably.
Okay, so the parallels are baked into the cosmos, but longitude, those vertical lines, the meridians, that's different. That's more man-made.
Precisely. It's fundamentally about time. See, the Earth spins, right? 15 degrees every hour.
Okay.
So to know your longitude, you need two pieces of time information at the same instant. You need your local time right where you are.
Which you can find easily enough when the sun's highest in the sky. That's local noon.
Yep. But the killer part is you also need to know the exact time back at a known reference point. Say your home port, like London or Lisbon.
Ah, right. So if my sun says it's noon, but I somehow know it's 3 p.m. back in London.
Then you know you're 3 hours west of London. 3 times 15. 45 degrees west longitude. Simple calculation.
If you know the London time.
And that was the absolute crux of the problem. How do you carry perfectly accurate London time on a ship that's pitching, rolling, going through wild temperature swings for months on end?
The early clocks just couldn't handle it.
Not even close. Pendulums were useless with the ship's motion. Temperature changes made metal expand and contract, throwing everything on.
And the oils they used for lubrication?
Yeah, they'd thicken in the cold or get too thin in the heat. Total nightmare for precision.
And this wasn't just academic. The cost of not knowing your longitude was horrifying. We're talking mass death.
Absolutely. The sources really hammer this home. The 1707 Scilly Isles disaster, it looms large.
It was a catalyst, wasn't it?
Definitely. 4 British warships, nearly 2,000 sailors lost, just smashed onto the rocks off the coast of Cornwall.
Because they thought they were safely out in the Atlantic, miles away, but their longitude was wrong.
Terribly wrong. And that story about the Admiral, Sir Cloud Disley Shovel,
Yeah.
it's chilling.
The sailor who tried to warn him.
Yeah. Just a common sailor, apparently keeping his own rough log, his own dead reckoning. He had a gut feeling, maybe based on his own calculations, that they were way off course, dangerously close to land.
He went to the Admiral.
And Shovel, well, he basically told him to shut up. How dare an ordinary sailor question his officer's navigation? Accused him of inciting mutiny.
And had him hanged. Right there on deck.
Hanged him on the spot. Hours later, the ships hit the rocks. 2,000 men drowned because of that refusal to listen, that reliance on flawed methods.
Wow. That really underscores the desperation. It wasn't just about trade routes. It was life and death on a massive scale.
And that disaster, that shock to the system, directly led Parliament to act. The Longitude Act of 1714.
This is where the big prize comes in.
The really big prize. £20,000,
Yeah.
which was, an astronomical sum back then. Millions in today's terms.
And the requirement.
A practical method to determine longitude at sea accurately to within half a degree. That's about 30 nautical miles at the equator.
Okay, so the challenge is set, the money's on the table, and basically two main paths emerge, right? Two competing philosophies.
Exactly. Path A was the astronomer's route, the clockwork universe approach. This was favored by the scientific elite, Isaac Newton, Edmund Halley. They were convinced the answer had to be in the heavens.
It feels logical for them, I guess. Look up.
Right. Galileo had actually suggested using the moons of Jupiter. Their eclipses happen very regularly, like clockwork.
But
Try using a telescope powerful enough to see Jupiter's tiny moons from the deck of a rolling ship. Impossible.
okay, so Jupiter's out. What then?
They focused on the lunar distance method. The idea was to use our own moon as a kind of celestial clock hand moving against the background of the fixed stars.
Sounds complicated.
Oh, incredibly. First, you needed new, very precise instruments, like the sextant, to measure the angle between the moon and a specific star, even with the ship moving. Second, you needed insanely detailed data. Star charts, the Astronomer Royal, Flamsteed spent like 40 years mapping stars for this. And then lunar tables, huge books predicting the moon's exact position for basically every hour of every day. People like Mayer and Euler crunched those numbers.
So you're on deck, it's probably rough, you're juggling a sextant, trying to get these angles. Then you pull out this massive book.
And then you sit down for about, 4 hours of complex trigonometric calculations.
4 hours for one longitude reading.
If you were good and the weather cooperated. And even then, the accuracy was maybe just meeting the prize requirement, around 30 miles. It worked, kind of, but it was brutally difficult.
Okay, I see why that wasn't exactly the dream solution, the sheer effort involved.
And the desperation for any solution led to some, let's say, creative ideas.
Like the wounded dog.
Oh, yeah, the powder of sympathy. You have to love the weird detours science takes.
Remind me how that was supposed to work.
Okay, so the theory was, you wound a dog before the ship sailed. Keep the dog on the ship. Back home, someone takes a bandage from the dog's wound and dips it into this magical powder of sympathy precisely at noon each day.
Yeah.
The idea was through some kind of sympathetic connection.
Action at a distance.
Right. The dog on the ship, miles away, would feel a pang from the powder and yelp. Exactly at noon, London time.
That's wow. Just wow. Shows how impossible the real solution seemed, I guess.
It really does.
Yeah.
Which brings us perfectly to path B, the mechanical clock, the timekeeper.
The obvious idea, right? Just carry the home time with you in a box.
Obvious, intuitive, but dismissed by almost everyone because, well, no clock had ever worked reliably at sea. Pendulums failed, metal warped, oil failed. Why would this time be any different?
Enter the unlikely hero, John Harrison. Not an astronomer, not an academic from Cambridge.
Nope. A carpenter, a self-educated clockmaker from Yorkshire. And he approached it not as an astronomy problem, but as an engineering problem.
He didn't just build one clock, did he? He iterated H1, H2, H3. These were huge machines.
Massive. He knew he had to conquer the enemies of timekeeping at sea.
Yeah.
Friction, temperature changes, and the ship's motion.
And he used wood in clever ways.
Ingeniously. His early clocks used a lot of lignum vitae. It's this tropical hardwood that's naturally oily, so it basically self-lubricates. That tackled the problem of temperature-sensitive oils gumming up.
Clever. What about friction?
He invented the grasshopper escapement, a mechanism that controlled the release of power to the clock's gears with almost no sliding friction. It was brilliant.
And temperature.
Yeah.
Metal expanding and contracting.
He tackled that too. For his land-based clocks, he invented the gridiron pendulum, alternating strips of brass and steel. They expand at different rates, so they cancel each other out, keeping the pendulum's length constant.
That's still used, isn't it?
The principle is, yeah. And for his sea clocks, particularly H3, he developed the concept of the bimetallic strip. Two different metals fused together that bend predictably with temperature changes, automatically compensating. Like in a modern thermostat, he was way ahead of his time.
Decades of work on these huge machines, H1, H2, H3, and then he does something unexpected for H4.
Totally unexpected. He shrinks it. H4 wasn't a giant sea clock. It was essentially a large pocket watch, about 3 pounds, finished in 1759.
And inside, more innovation.
Absolutely. To fight friction at that small scale, he used jewels, tiny diamonds, and rubies as bearings for the delicate moving parts. It was exquisite. Even the artist Hogarth called it one of the most exquisite movements ever made.
So the proof is in the pudding. Did they work at sea?
Oh, yes. Even his first big one, H1, on a trip to Lisbon back in 1736, it corrected the ship captain's dead reckoning estimate by 60 miles.
60 miles. That could easily be the difference between safety and shipwreck.
Exactly. But H4, the watch, was a real star. They sent it on a test voyage to Jamaica in 1761, 81 days at sea.
And the result?
It lost only 5 seconds. 5 seconds in nearly 3 months. The total error in calculating longitude based on H4 was less than 10 miles.
10 miles. The prize required accuracy within 30 miles.
Precisely. He hadn't just met the requirement, he'd smashed it. 3 times better. Logically, he should have gotten the prize right then and there.
But he didn't. Which means we move from the workshop into, well, politics and rivalry.
You got it. Harrison's simple, brilliant mechanical solution was a direct threat to the entire astronomical establishment. They had sunk decades of effort and public money into the lunar distance method.
And Harrison's main opponent was?
Reverend Neville Maskelyne, the Astronomer Royal. And crucially, a key member of the Board of Longitude, the very committee judging the prize.
Oh, that sounds like a conflict of interest.
A massive one.
Yeah.
Maskelyne genuinely believed Harrison's success with H4 must have been a fluke, a lucky accident. He was deeply invested professionally and financially in the lunar method. He just started publishing the Nautical Almanac, the essential tables for his method.
So the judge was basically competing against Harrison.
It looks an awful lot like it. The board, heavily influenced by Maskelyne, just dragged their feet. They eventually admitted H4 was sufficiently correct, but refused to hand over the full 20,000 pounds.
What did they demand instead?
Unreasonable things. First, Harrison had to reveal all his secrets, every drawing, every mechanism. He had to explain exactly how H4 worked.
Give away his life's work.
Yes. And then they demanded he supervise the construction of 2 more copies, just to prove it wasn't some unique, unrepeatable miracle.
Humiliating.
It gets worse. After he painstakingly documented everything, even having to dismantle H4 under oath for inspection, they seized the watch
Seized it.
and sent it straight to his rival, Maskelyne, at the Royal Observatory for further testing.
You cannot be serious.
Oh, yes. Maskelyne kept it for 10 months, subjected it to deliberately unfair tests, messing with temperatures erratically, and then issued a report saying H4 couldn't really be trusted and his lunar method was still superior.
Okay, this is beyond scientific disagreement. This sounds like outright sabotage. What could Harrison do?
He'd had enough of the board, he was getting old, he felt cheated, so he went over their heads. He appealed directly to the king.
King George III.
The very same. George III was actually really interested in science and clocks. He even had his own private observatory. He listened to Harrison's story. He was apparently furious at how the board had treated this brilliant inventor. The sources quote him saying something like, "By God, Harrison, I will see you righted."
Royal intervention. Did it work?
It did. The king's support basically forced Parliament's hand. In 1773, they bypassed the Board of Longitude entirely and awarded Harrison a separate sum, £8,750, not technically the Longitude Prize, but a parliamentary bounty acknowledging his incredible achievement. He finally got recognition and a good chunk of money near the end of his life.
Justice of a sort. But maybe the ultimate validation came from someone else.
You could definitely argue that. The ultimate sea trial, you might say, came from Captain James Cook.
The great explorer.
Exactly. On his second epic voyage, from 1772 to 1775, Cook took a copy of H4, made by another clockmaker, Larkham Kendall. It's often called K1.
And Cook actually used it.
He relied on it heavily. Cook himself was an expert navigator, skilled in the lunar method too, but he quickly saw how much easier and more accurate the chronometer was.
What did he say about it?
He raved about it in his journals, called K1, Our Trusty Friend the Watch, and Our Never-Failing Guide. He used it to make incredibly accurate charts of the Pacific Islands, maps that were used for generations. That endorsement was huge.
So Cook proves it works wonders in the real world. What happens then?
The floodgates open. Chronometer making becomes a real industry. Other brilliant makers like John Arnold and Thomas Earnshaw jump in, refining the designs, making them cheaper, more robust. Within a few decades, marine chronometers became standard equipment on naval and merchant ships.
Harrison's mechanical approach had clearly won.
No question. It was simpler, faster, and ultimately more accurate than wrestling with lunar distances for 4 hours.
But here's the twist, right? The irony.
The beautiful irony. Even though Harrison's clock won the practical battle, the astronomers, specifically Maskelyne, ended up defining the map of the world.
Oh, so?
Because Maskelyne's Nautical Almanac, those tables for the lunar method, were all calculated using the meridian line running through the Royal Observatory at Greenwich as the 0 point, the starting line.
Okay.
So even when sailors started relying on Harrison's chronometers, they still needed a reference time. The chronometer told them Greenwich Mean Time. And sometimes they'd still use the almanac or astronomical observations to double-check or rate their chronometer against. You guessed it, Greenwich time.
Ah, so Greenwich became the default reference point simply because Maskelyne's widely used tables were based on it.
Pretty much. It became the common standard through sheer established practice, even though the method it was originally designed for became secondary.
Which leads us to
the 1884 International Meridian Conference in Washington, D.C. They needed to officially agree on a single prime meridian for the whole world, 0 degrees longitude. And because so many charts and timekeeping practices already use Greenwich,
they just made it official.
They voted, and Greenwich won. So the time standard we still use, GMT, or Coordinated Universal Time, UTC, which is based on it, and the line dividing east from west on every map, owes its existence, indirectly, to the work of the guy whose method lost the longitude battle,
Yeah.
but whose reference point stuck.
That's fascinating. So Harrison, the carpenter, gives us the ability to measure longitude accurately anywhere, anytime.
This incredible mechanical box solves the great scientific problem of the age, beating the academic establishment.
But the starting line for that measurement, the prime meridian itself, running through that courtyard in Greenwich, its position is essentially an artifact of the losing side's paperwork.
You could definitely see it that way.
Yeah.
A legacy of Maskelyne's tables, cemented by convenience and history.
So here's something to chew on. Harrison's genius gave us the means to master time and space on the globe. But the way we actually define that space, the arbitrary line from which we measure all longitude and indeed global time, that ultimately came down to historical habit and essentially a political agreement in 1884. Makes you think, doesn't it? Our whole precise grid system rests on a line chosen, in part, by the legacy of the method that didn't win.